Hello guys, I am Utsav Yadav and I am here again with our new chapter of data science series is Naïve Bayes Classification. So, firstly, we have to understand what is Naïve Bayes Classification. So, we go through the introduction of Naïve Bayes Classification. Naïve Bayes is a simple yet powerful probabilistic classifier based on Bayes theorem with the assumption that the features are conditionally independent given the class level. Despite the seemingly unrealistic assumption of conditional independence, naive-based classifiers often perform very well, particularly in text classification. The tasks like spam filtering, sentiment analysis, and medical diagnosis. The key concept of naive Bayes. Probabilistic classifier, Bayes theorem, independence assumption. Probabilistic classifier. Naive Bayes is a probabilistic classifier because it predicts the probability distribution of the class level. For a given input, x is equals to x1, x2 to xn. X is equals to x1, x2 dots xn. X is equals to x1, x2 up to xn. Naive-Bayes compute the posterior probability of each class CCC given the observed features. Bayes theorem. Naive-Bayes classifiers use Bayes theorem to make decisions about which class is most likely given the data. Independence assumption. The naive-Bayes classifier makes the naive assumption that the features are conditionally independent given the class. This assumption greatly simplifies the model, allowing for efficient computation. Here are the applications of naive-Bayes classification. First, test classification. We have further classification in test classification are spam filtering, sentiment analysis, document categorization. Spam filtering used to classify emails as spam or not based on word patterns. Sentiment analysis analyze text to determine sentiment. Document categorization classifies documents into categories like sports, politics, or technology. Second application of naive-Bayes classification is medical diagnosis. Helps in diagnosing disease based on symptom, medical test, or patient history. Third application, recommendation system, used in recommending products, movies, or music based on past user behavior. Example, Netflix, Amazon. Fourth application is fraud detection. Identifies fraudulent transaction by classifying them as legitimate or suspicious. Fifth application, real-time data analysis. Used for real-time prediction in scenarios like stock market prediction or weather forecasting. Sixth application, anomaly detection. Detect outliers or abnormal patterns in data. Seventh application, speech recognition. Classifies audio feature to recognize speech commands. Example, voice assistant like Siri. Image recognition. Used for basic image classification tasks like recognizing handwritten digits. Now, what are the advantages and disadvantages of name-based classification? Advantages: simplicity, efficiency, and performance. Name-based is simple to implement, easy to understand, and computationally efficient. Efficiency. It is particularly fast in both training and prediction, even with high-dimensional datasets. Performance. Despite its simplifying assumptions, it often performs surprisingly well, especially in high dimensional problems like text classification, example email spam filtering. Disadvantages: strong independence assumption and poor performance with correct correlated features. The major drawback is the model assume features are independent, which is often not the case in real-world data. Poor performance with correlated features. If the features are highly correlated, naive Bayes may not perform as well compared to other models like decision trees, SVMs, or ensemble methods. Now we have to understand the most important part of naive-Bayes classification is Bayes theorem. Bayes theorem provides the foundation for naive-Bayes classification. It describes the relationship between conditional probabilities. Given some data, feature XXX, Bayes theorem updates the probability of a class CCC based on the observed data. The formula for Bayes theorem is probability of C by X is equal to probability of X by C probability into probability of C upon probability of X, where probability of C by X into probability of C by mid X into probability of C by X is equal to the posterior probability of class CCC given the feature XXX, and probability of X by C probability into probability of X by mid C into probability of X by C is equal to the likelihood or the probability of observing the feature XXX given the class CCC. Now, probability of C into probability of C into probability of C is equal to the prior probability of class CCC, which reflects how likely a class is before observing the data. Now, probability of x into probability of x into probability of x is equal to the total probability of observing the features xxx, which acts as a normalizing constants. Naive-Bayes classifiers compute the post- posterior probabilities for each possible class and select the class with the highest post- posterior probability as the predicted level. Now, as we move ahead from Bayes theorem, we got our new topic, maximum a posterior hypothesis. The maximum a posterior hypothesis is a decision rule used in naive-Bayes classification to select the most probable class for a given observation XXS. The goal is to find the class CCC that maximizes the posterior probability, probability C by X, probability into probability C by mid X into probability C by X. That is the class that is most likely given the observed feature. The map rule can be written as C is equals to argument max probability C by X. Using Bayes theorem, we can rewrite this as C is equal to argument max probability of X by C into probability C upon probability of X. Since probability of x is constant for all classes, it can be ignored during the maximization process. C is equals to argument max probability of x by c into probability of c. Thus, we compute the likelihood probability of x by c into probability of x by mid c into probability of x by c, and the prior probability of C into probability of C into probability of C for each class, and choose the class that maximizes this product. This is the map estimation in naive Bayes. Now, class conditional independence. One of the key assumptions in naive-Bayes classification is class conditional independence. This assumption states that given the class CCC, all the feature x1, x2 up to xn x1, x2 dots xn are independent of each other. This is often unrealistic in practice, but in many cases, naive-Bayes still perform surprisingly well despite this assumption. The class conditional independence assumption simplifies the likelihood calculation. Instead of computing probability of x by c into probability of x by mid c into probability of x by c as a multidimensional distribution. Naive-Bayes assumes that probability of x by c is equal to probability of x1 by c into probability of x2 by c up to probability of xn by c. This makes the naive-Bayes model computationally efficient as it decomposes the problem into the product of probabilities for each feature conditioned on the class. For example, in spam detection, the presence of certain words in an email is assumed to be independent of the presence of other words, given whether the email is spam or not. Now, the last topic of our naive Bayes is application of naive Bayes classification. Naive Bayes in Python. Python provides an excellent ecosystem for machine learning with libraries like skitlearn, which involves a naive Bayes implementation. Below is a detailed step-by-step guide on how implement naive Bayes in Python using skitlearn. Example: Naybase with the Irish dataset. Firstly, we have to install a necessary library is pip install skitlearn numi pandas. Now we can see the Python code for application of Naybase classification. So this is our Python code example. We load the Irish dataset, which is classic dataset with 150 samples and 4 feature sepal length, sepal width, petal length, and petal width. We split the dataset into training and testing subjects. 70% training, 30% testing. We create a Gaussian name-based model, which assume the feature follow as Gaussian distribution. After training the model on the training data, we use it to make prediction on the test data and evaluate its currency. So firstly, we have to import necessary libraries in our Python code. Then data is equal to load iris, x is assigned to data.data, y is assigned to data.target. And by running this code, we get output accuracy is 95.556%. So guys, in this video, I completely discussed about our chapter 8 of data science name-based classification. So if you find this video helpful, please like my video, subscribe my channel and share this video with your friends. Thanks for watching our video.